In the heart of Western Germany, there's a place that feels like a dream caught between worlds. A theme park sprawls across a quiet stretch of land, its carousel spinning with laughter, its roller coaster slicing through the sky, and families weaving through the crowds with cotton candy in hand. But then, you see it. A towering, concrete behemoth looming over the festivities like a ghost from another era. It's a cooling tower, the kind you'd expect to find at a power plant, not a playground. This isn't just any amusement park. It's built on the ruins of an abandoned nuclear reactor, a relic of a forgotten ambition that promised to rewrite the rules of energy. This wasn't your typical nuclear plant, humming along to produce electricity for homes and factories. No, this one was designed to do something almost magical, something that feels like it belongs in a science fiction novel. It could create more fuel than it consumed, like a fire that grows stronger the longer it burns. And yet, this reactor never hummed to life, not for a single moment. It stands silent, a monument to a dream that fizzled out. But why? Why did we turn our backs on a technology that promised to stretch our resources and tackle the nagging problem of nuclear waste? That toxic legacy we've been piling up with nowhere to go? This is a story of hope, fear, and the choices that shape our future. It's a story that begins in a desert, under a sky vast enough to hold the wildest of dreams. Picture it, Idaho, 1951. The world is still reeling from the scars of war, and the air crackles with the promise of a new age. In a remote corner of the desert, a small reactor named EBR-1 flickers to life. It's not just generating electricity, it's making history. For the first time, a nuclear reactor powers a motion picture camera, capturing the moment with energy born from splitting atoms. But that's not what makes this moment unforgettable. This reactor, this humble machine in the middle of nowhere, is doing something extraordinary. It's breeding fuel. As it burns uranium, it creates more fissile material than it uses, like a farmer planting seeds that yield a harvest greater than what was sown. Nuclear scientists called it breeding, a word that carried the weight of a revolution. Back then, the world believed uranium was scarce, a precious resource that would run dry if we leaned too heavily on nuclear power. The idea of a reactor that could stretch this finite resource, turning the useless into the useful, felt like a glimpse into a boundless future. From the very beginning, says Nick Turan, a nuclear engineer who spent over a decade designing reactors, we thought breeders were the long-term future. It wasn't just a theory. It was a vision that drove scientists to imagine a world where energy was no longer a question of scarcity, but of ingenuity. To understand why this mattered, we need to dip our toes into the world of atoms. But don't worry, I'll keep it simple. Imagine a chunk of natural uranium, a dull, heavy metal that holds secrets in its core. It's made up mostly of two types of atoms, uranium-235 and uranium-238. The 235 is the star of the show. When a neutron slams into it, the atom splits, releasing a burst of heat and sending more neutrons flying like sparks from a fire. Those neutrons hit other 235 atoms, and the chain reaction begins, producing the heat that spins turbines and lights up cities. But here's the catch. Only 0.7% of natural uranium is this useful uranium-235. The rest, the overwhelming majority, is uranium-238, which doesn't split easily when a neutron hits it. Instead, it soaks up the neutron like a sponge, offering no energy in return. It's like having a gallon of milk but only being able to use the cream. Scientists looked at this and saw a challenge. What if we could unlock the energy trapped in that 99.3% of uranium-238? If we could, we'd multiply the world's nuclear fuel supply 100-fold, turning a scarce resource into an abundant one. That was the promise of fast reactors, the strange machines that once dotted the globe, from Idaho to Germany to Japan. These fast reactors were a different breed, Unlike the slow reactors we know today, which use water to cool the core and slow down neutrons, fast reactors relied on liquid metals, often sodium, to carry heat away. Sodium doesn't slow neutrons down. It lets them zip around at breakneck speeds, and those fast-moving neutrons are the key. When they crash into uranium-238, something remarkable happens. The 238th captures the neutron, transforms first into neptunium, then into plutonium, a material that splits as eagerly as uranium-235. This plutonium can be extracted, processed, and turned into fresh fuel, ready to power the reactor again. It's a cycle that feels almost alchemical, turning the useless into the essential. For a while, the world was captivated. Fast reactors sprang up in the United States, France, Japan, and beyond, each one a testament to human ambition. But if they were so promising, why are they now little more than footnotes in history? Why does that cooling tower in Germany stand silent? A curiosity for theme park visitors rather than a beacon of progress? The answer lies in a tangle of fear, politics, and practical realities. In the late 1970s, the world's mood shifted. Nuclear power, once a symbol of hope, began to carry a darker shadow. The plutonium produced by fast reactors wasn't just fuel, it was also the stuff of nuclear weapons. The idea of a plutonium economy, where this material was routinely extracted and processed, sparked fears of proliferation. What if it fell into the wrong hands? In the United States, President Jimmy Carter made a fateful decision in 1977, halting a major fast reactor project to curb the risk. In Germany, protests erupted, voices rising against the reactor that would later become a theme park oddity. By 1991, it was abandoned, its billions in costs swallowed by time. Other countries pressed on, France and Japan took the risk, and Russia still runs 2 large fast reactors today. But the tide was turning. Sodium, the coolant of choice, proved to be a headache. It reacts violently with water or even moisture in the air, leading to accidents like the one at Japan's Manju reactor in 1995. A sodium leak triggered a fire, and the reactor sat idle for nearly 15 years. Even France's Superphénix, the largest fast reactor ever built, was plagued by technical hiccups, from sodium leaks to a collapsed roof buried under snow. Operating costs soared, and the dream began to fade. But there was another twist. Back in the 1950s, scientists thought uranium was rare, a resource to be hoarded. By the 1980s, it was clear they'd been wrong. New deposits were found, and mining uranium-235 became cheaper than breeding and processing plutonium from 238. Why wrestle with exotic coolants and complex reprocessing when you could just dig up more fuel? Fast reactors, once the darling of the nuclear world, were sidelined, their potential locked away like a book gathering dust on a shelf. Yet, as the world faces new challenges, that book is being opened again. The reasons are as urgent as they are compelling, and they pull us into a future where the ghosts of the past might just hold the key to survival. The world turned its back on fast reactors, but the story didn't end there. It couldn't, not when the stakes are so high and the ground beneath our feet is shifting. Imagine standing at the edge of a cliff, the wind howling, the horizon glowing with the faint promise of dawn. That's where we are now, grappling with a planet that's warming faster than we can keep up, where every choice we make about energy feels like a race against time. Fast reactors, those strange, almost mythical machines, are creeping back into the conversation, not because we've run out of uranium, but because they might hold the key to 2 of humanity's biggest headaches: climate change and nuclear waste. The dream that flickered out in the deserts of Idaho and the theme parks of Germany is stirring again, and it's pulling us into a future that's equal parts hope and uncertainty. This isn't just about powering homes or lighting cities, it's about rewriting the rules of what we thought was possible and confronting the ghosts of our fears along the way. Let's start with climate change, the shadow that looms over every decision we make. Nuclear power has always been a strange beast, feared for its risks, revered for its potential. Unlike coal or gas, it churns out electricity without choking the air with carbon dioxide. It's a steady, relentless source of energy, running day and night, unmoved by clouds or calm winds. But for decades, nuclear's growth has stalled, plateauing since the early 2000s as accidents like Chernobyl and Fukushima fueled public distrust. Yet, at the 2023 COP Climate Conference, a bold promise was made to triple nuclear capacity by 2050. It's a goal that feels both audacious and necessary, a call to arms against a warming world. But here's the rub. If we start building hundreds of new reactors, the demand for uranium will spike, fuel costs will climb, and the scarcity fears of the 1950s will creep back in. That's where fast reactors come in. They don't just burn fuel, they multiply it, squeezing every drop of energy from uranium we thought was useless. If we're going to see a big push for nuclear, says Paul Wilson, a nuclear engineer who builds models to untangle the future of energy, the ability of breeders to get so much more out of that fuel will start to make sense. It's not just about keeping the lights on, it's about stretching our resources to meet a crisis that doesn't wait. Across the globe, the embers of this idea are glowing again. In China, a demonstration fast reactor hums in low-power mode, a testing ground for a second, larger one under construction. India, too, is moving forward, loading fuel into a prototype reactor that's been in the works since 2004, with plans to fire it up by the end of 2025. These aren't just experiments. They're statements of intent, driven by a hunger for energy independence and a desire to make the most of limited resources. Even private companies are stepping into the fray, backed by names that carry weight. Bill Gates, through his company TerraPower, has broken ground on a fast reactor in Wyoming, a project that promises to power hundreds of thousands of homes with greater efficiency than the reactors we know today. It's a vision that feels like it's ripped from the pages of that 1951 dream, but updated for a world that's learned hard lessons. These new reactors aren't just about breeding fuel, they're about proving that nuclear can be a cornerstone of a cleaner future, a way to fight climate change without sacrificing reliability. But there's another reason fast reactors are clawing their way back, and it's even more tantalizing. Nuclear power has a dirty secret: waste. The spent fuel rods we pull from reactors are radioactive for tens of thousands of years, a legacy we've been shoving into temporary storage because we don't know what else to do with it. It's like bearing a problem and hoping future generations figure it out. Fast reactors, though, offer a different path. They don't just breed new fuel, they can burn the waste we've already created. Paul Gauthier, CTO of the French nuclear company HEXANA, puts it simply, it's only waste if you waste it. Hexana is developing a fast reactor designed to run on the depleted fuel from conventional reactors, recycling what we thought was useless. In a traditional reactor, you mine uranium, enrich it, burn it, and store the leftovers. But fast reactors flip the script. They take that spent fuel, rich in plutonium, and use it again and again and again. The Superphénix, France's massive fast reactor from decades ago, proved this wasn't a pipe dream. It ran on recycled fuel. And the waste that comes out? It's less toxic, its radioactivity fading in hundreds of years instead of millennia. It's not a perfect fix, but it's a step toward a future where we're not passing a ticking time bomb to our grandchildren. This idea of a circular nuclear economy is intoxicating. Imagine a world where we mine less uranium, leaning instead on the fuel we've already used. Fast reactors could make that real, turning a linear process, mine, burn, store, into a cycle that keeps giving. They could reduce the mountains of waste piling up in storage sites, from the deserts of Nevada to the bunkers of Europe. But here's where the dream gets complicated. Recycling fuel isn't like tossing a can into a bin. It's a messy, expensive process. To use spent fuel, you have to chemically reprocess it, separating out the plutonium and turning it into new fuel pellets. This isn't just technically challenging, it's a logistical nightmare. It takes a lot of care, says Paul Wilson, because it comes with a lot of radioactive species. The facilities to do this are few and far between, and building more would mean creating an entirely new industry. Right now, it's cheaper to mine fresh uranium and park the waste in storage than to wrestle with reprocessing. And that's not the only hurdle. Fast reactors themselves are costly to build. Their sodium coolant's still a temperamental beast compared to the water used in conventional plants. The ghosts of Manju and Super Phoenix linger, reminding us that ambition comes with risks. Yet, the world is changing, and so is the math. As uranium prices creep up and the pressure to decarbonize intensifies, the economics of fast reactors start to look less daunting. Countries like China and India aren't just building reactors. They're betting on a future where energy independence and sustainability go hand in hand. Private innovators like TerraPower are pushing the boundaries, designing reactors that are safer, more efficient, and less prone to the sodium mishaps of the past. But the clock is ticking. Nuclear reactors take years, sometimes decades to build. Hexena aims to have its first reactor running by 2035, but even then, scaling up a global network of fast reactors and reprocessing plants could take a century. A century. That's a timeline that feels like a lifetime when we need clean energy now, yesterday, last week. And then there's the old fear, the one that killed the dream in the 1970s. Proliferation. The plutonium that fast reactors produce is still the stuff of nightmares, a material that could be weaponized if it falls into the wrong hands. Every step toward this future is a step on a tightrope, balancing hope against caution. This is where the story of fast reactors becomes more than a tale of science. It's a mirror held up to humanity. We're at a crossroads where the choices we make today will echo for generations. Fast reactors could be a game changer, a way to stretch our resources and clean up our mess. But they're not a silver bullet. They demand patience, investment, and a willingness to confront risks we've shied away from before. As the carousel spins in that German theme park, under the shadow of a silent cooling tower, it's a reminder of what we've lost and what we might still gain. The question isn't just whether we can bring fast reactors back, it's whether we have the courage to try. The cooling tower still stands in that German theme park, a silent giant watching over the laughter and screams of roller coaster riders. It's a relic of a dream that never took flight, a reminder of what could have been and what might still be. The story of fast reactors is a saga of human ambition, of reaching for the stars only to stumble over our own fears and flaws. But as the world grapples with a warming planet and a growing pile of nuclear waste, that old dream is whispering to us again. It's not just about powering cities or stretching uranium reserves. It's about rewriting the story of energy, about finding a way to live with the choices we've made. Fast reactors could be a bridge to a cleaner, more sustainable future, but the path is fraught with challenges, technical, political, and moral. This final chapter isn't about easy answers or tidy resolutions. It's about the courage to face the unknown, the patience to build something enduring, and the humility to learn from the past. As we stand at this crossroads, the question looms: can we bring this forgotten technology back, and should we even try? The promise of fast reactors is as intoxicating now as it was in 1951, when EBR-1 flickered to life in the Idaho desert. They offer a vision of a world where we mine less uranium, where the waste we've buried in temporary tombs becomes fuel for a new generation of reactors. Imagine a cycle where energy doesn't end in a stockpile of radioactive leftovers, but loops back, feeding itself like a perpetual motion machine. The science is sound. France's Super Phoenix showed it could work. running on recycled fuel and producing waste that's less toxic, less eternal. Companies like Hexana in France and TerraPower in the United States are betting on this future, designing reactors that could power heavy industries or entire cities while eating through the waste we've accumulated. China and India are pushing forward too, their prototype reactors inching closer to reality. At the 2023 COP conference, the call to triple nuclear capacity by 2050 lit a spark, and fast reactors are part of that vision, a way to stretch resources and keep the lights on without choking the planet. It's a dream that feels like it could change everything. A world where nuclear power isn't just clean, but regenerative. A solution that doesn't just delay problems, but solves them. But dreams don't come cheap, and this one carries a heavy price. Reprocessing spent fuel is the heart of the fast reactor's promise, but it's also its Achilles heel. Picture a lab where scientists in hazmat suits handle materials so radioactive they glow with an eerie intensity. Separating plutonium from spent fuel isn't like recycling plastic. It's a delicate, dangerous dance with elements that can kill. The process is expensive, far more costly than mining fresh uranium, and it requires facilities that are rare and tightly regulated. It's not as simple as making fresh fuel, says Paul Wilson, his voice carrying the weight of someone who's seen the numbers. There are only a handful of reprocessing plants in the world, and building more would mean creating an entirely new industry from scratch. It's not just about money, it's about time. Nuclear reactors take years to design, approve, and construct. Hexana's goal of a working reactor by 2035 is optimistic, but even if they succeed, scaling up to a global network of fast reactors could take decades, maybe a century. A century. That's a timeline that feels like a lifetime when the planet is warming now, when storms are growing fiercer and summers hotter by the year. We need solutions yesterday, and fast reactors, for all their promise, move at the pace of a glacier. Then, there's the shadow that's haunted this technology from the start: proliferation. The plutonium that fast reactors produce isn't just fuel. It's the raw material for nuclear weapons. In the 1970s, this fear stopped projects in their tracks, from Jimmy Carter's decision in the U.S. to the protests that shuttered Germany's reactor before it ever ran. That fear hasn't gone away. Every ton of plutonium separated in a reprocessing plant, countries like Russia, with their two operating fast reactors, have accepted this risk, but others hesitate. The world is different now, with new players and new threats, and the idea of a plutonium economy still sends shivers down spines. Security would need to be ironclad, oversight relentless. And even if we could manage that, there's the sodium problem. The liquid metal that makes fast reactors possible is a temperamental beast, reacting violently with water or air. The memory of Japan's Manju reactor, shut down for 15 years after a sodium fire, lingers like a warning. New designs promise safer systems, but the past teaches us to be wary. Every step forward is a gamble, a bet that we can outsmart the mistakes we've made before. So, should we give up? Should we let fast reactors fade back into obscurity, a footnote in the history of what might have been? The answer isn't simple because the stakes are too high for easy choices. Fast reactors aren't a silver bullet. They're a long-term bet, a vision that demands patience and resolve. There are hurdles, says Nick Turan, but that doesn't mean we shouldn't try. He's right. The potential is too great to ignore. A world where we mine less uranium, where nuclear waste becomes a resource rather than a burden, is worth fighting for. But it can't distract us from the solutions we have now. Solar panels gleaming in the sun, wind turbines spinning in the breeze, and conventional nuclear plants humming along. These are the tools we can deploy today, while fast reactors remain a promise for tomorrow. The challenge is balance, pursuing the dream without losing sight of the urgent. It's about building bridges to a future we can't yet see, while keeping the lights on in the present. As the sun sets over that German theme park, the cooling tower casts a long shadow across the carousel. It's a symbol of what we dared to dream and what we failed to achieve. But it's also a reminder that failure isn't the end. It's a lesson. Fast reactors are a story of human ingenuity, of reaching for something bigger than ourselves. They're also a story of caution, of the risks we take when we push the boundaries of what's possible. Today, as we stand on the brink of a climate crisis, that story feels more relevant than ever. The question isn't just whether we can bring fast reactors back, it's whether we have the will to try, the wisdom to do it safely, and the vision to see it through. What do you think? Should we resurrect this forgotten technology or let it rest in the shadow of that cooling tower? The choice is ours, and the future is watching.